This is the first lesson for our final chapter for AP Calculus. And in this chapter, we're going to be tying together some ideas that we've seen throughout the course. Just in general, you could say we're going to be doing some things called accumulator problems. And I want to start off by just the first example of that being the idea of filling up a bathtub, where you've got some sort of faucet that's flowing water into your bathtub, and you might have that faucet just flowing, very, very slowly, just a little trickle of water going in. But even if it's a trickle, you'd actually be filling up your tub. The tub level would be getting higher and higher and higher. Or you could put that faucet on super fast, and you could fill the tub just at a faster rate. Either way, you'd be filling the tub up, but just one would get the job done faster. So let's kind of just formalize this here, and we can say, all right, we've got our faucet that's flowing water into the tub, and it's operating at some rate, and ultimately there's a certain amount of water that's just sitting here in our bathtub. And we're going to use the letter R to talk about the faucet, how fast it's flowing water in. That might be in kilograms per second, if it's a really big faucet anyways. And then A is going to talk about how much water's actually in the bathtub. And those two ideas, the flow rate R and the amount of water in the bathtub, they're just tied together with derivatives and integrals. The rate is all about the speed that you're getting water into the bathtub. This is how much you've opened the faucet up. This is your kilograms per second. And that rate is really just the derivative of how much stuff is in your bathtub. So you might be measuring, how much water, how much stuff is in there in kilograms. And if we were to do a time derivative in seconds, then we would know what the rate is for that faucet. But you can spin that idea around, and you can say, well, if I want to know how much stuff is there, how much water is there in my bathtub, I could actually go and just do the antiderivative of the rate. I could do the integral of the rate, right? So if my rate is in kilograms per second, and then I integrate with seconds, then I can actually find out how much water is in there. Give or take a constant, which is kind of all about how much water was in there at the beginning. Now, that's kind of great, using the word stuff and rate. Well, let's actually use the actual letters R and A and see what this would look like. You could say the rate at any time t is really it's just A prime. It's just the derivative of the A. If you want to get a little fancier, we can use the Leibniz notation here and say, yeah, it's just this derivative of A. It's nothing more than A prime. If you want to know what the A is, if you want to know how much amount of water there actually is in your tub, well, then you're going to have to integrate from one time of the day to another time of the day. From time 1 to time 2, we'll just be integrating our rate, dt, and that'll tell you how much amount of stuff there is in your tub. Oh, to within a constant, right? There's always kind of that plus c kind of issue. And I think we should probably just formalize this little plus c right now. And a great place to put this is actually on the front cover because there's some space right here. And this might be something that we come back to a fair bit. So just right on the front cover of our little notebooklet here, I just want to put down a couple of options that we've got as far as dealing with this c goes. If you only want to know, well, how much more water have I added to the bathtub? If you only want to know change in amount, then all you have to do is just integrate the rate from one time to another, and you'll be totally fine. So that would just be the integral from time 1 to time 2 of the rate dt. And that'll be great. That's your change in amount. But if you really want to know how much water, what the actual amount of water is in the tub, then you have to deal with the fact that there may have been water in the tub originally. So the actual amount at time 2, that's going to be the starting amount at time 1, because there may have been water in your tub already. And then we're going to accumulate more water from time 1 down to time 2. So this is actually going to be the final amount. Now we're going to throw a little fun name on this. Okay, if you have to find that final amount, if that's really what you want to do, the name we're going to give it just for fun is going to be named after some like World War II canned meat. We're going to call it the SPAM method. And I'll show you why. Okay, so if you're finding the final amount and you're doing this addition of the beginning with the stuff you're adding, sure, this is going to be, we're just going to jokingly call it the SPAM method. And that's going to stand for start, like how much water did you have in there at the beginning, plus, don't forget to add on the new water, the accumulation of the new water. So we'll call it the start plus accumulation method. We'll just say, oh yeah, you just have to spam it, right? If you're going to actually find out how much water is in there in the end. You know, visually, I guess it would be like this. There may have been, at the beginning of the day, there may have already been some water in the bathtub, right? There could have been some amount at time 1 at the beginning of the day. And then you might go and flow more water in for a little while. So you're going to add in a little layer of water. And that added in layer, that change in amount, that would be the integral of the rate dt. And then once you've added that additional amount on to the amount of water that was already in there in the first place, that's when you can go and find the actual final height, the final amount for the water. So that'll be our SPAM method. Okay, well I think we're ready to try this out. I'm noticing that the amount and the rate are off by a derivative. And so just like when we were doing those little chipmunk stories gathering up area under the graph, like a chipmunk gathering nuts, we would create a little legend. This little legend here could be super useful if you're trying to figure out some story and they're talking to you about the amount and they've only given you a picture of the rate that you're filling the tank. Things are just off by a derivative and you can just create a little scale at the beginning and then we're totally good to go. So on the next page, on page 3, let's talk about doing exactly that, about converting our thoughts between amount and rate. And remember, those two issues, those two columns here are off by a derivative. So let's say you're trying to figure out when you might have a critical point in the amount. So if you've got your bathtub and you're wondering, oh yeah, like when will I maybe possibly be having a maximum or a minimum amount of water in this bathtub? Right? What could a critical point be? Well, a critical point would be when the derivative of the amount is equal to 0. That could be when the water level is like hit a peak, or maybe it's gone down and it's hit a minimum, then you're about to fill it back up again. And so just based on our knowledge from way back in chapter 4, we would say if you want a critical point, then the derivative of that amount has to equal 0. If you wanted to know when there's a maximum amount of water in the bathtub, right? You know, when this water level actually hits some sort of peak, well then the derivative of the amount is actually going to have to equal 0, right? Because your graph of amount and time would have to hit a little flat spot like right there. So that could be this story right here where the derivative goes from positive to negative. And likewise, if you're draining the tank and you wanted to catch a minimum value for the water in the tank, then you'd be watching this derivative and you'd be saying, hey, does that derivative for the amount, does it ever make a switch from negative to positive? Because that's our first derivative test, our most common test for finding maximums and minimums. And if it goes a derivative from negative to positive, we'll have a minimum for sure. Well, what we're going to do in this chapter is say, well, what if we don't want to talk about the letter A? What if we want to talk about rate? Well, no problem. I've got my little legend here. A prime is just the rate. So we could convert all these stories into just stories about rate. We could say, oh, well, a critical point will be when the rate is equal to 0. A maximum would be when the rate of flow makes a little switch from positive to negative. Okay, and you might be wondering, well, what does that mean, to be negative? Well, you'd have to have a drain going on. Here's another way to look at it. Let's say you've got some sort of fuel tank, and if you've got fuel going into the tank, right? So down this pipe and into that tank, then you would say, oh, the rate is a positive. But if you're actually pumping fuel out of the tank, then you could say, oh, well, the rate for that tank is going to be a negative because we'll be dropping the fuel level inside the tank. So we could have one pipe and just be flowing water in and out, and that would work just fine. So this is how we could go and convert this story then from stories about amount to stories about rate. And if your rate went from negative, in other words, you're pumping fuel out, to switching over to a positive rate, which means, oh, geez, now we're starting to pump fuel into the tank. Then that switch over, when you're switching from pumping out to pumping in, that's when you'd have a minimum level of fuel in the tank, which intuitively makes sense. We don't use the second derivative test very often. That was that way of saying, hey, could I find a maximum in a more creative way? If I look for a maximum in some sort of graph, it could be a spot where it's a critical point, where it's flat, and maybe the graph is concave down. That would confirm that I've got a maximum. And the reverse, if you've got a flat spot in the graph, if you've got a critical point in the graph, which is this first row in the table, and if you know the graph of amount is concave up, then you would say, oh, then I know I've got a minimum. Okay, so that would be when A double prime for sure is equal to some positive value at that one critical point that you're testing. So how do you convert that over to working with rate? Well, it's actually pretty easy. A prime being 0, looking for that critical point in the story, well, that would just be when R is equal to 0, because A and R are off by a derivative. A double prime, not a problem, right? I can even go back to my little legend here. A double prime, that's just R prime. It's the speed that you're changing the rate. So if the R graph has a slope, right, the derivative of it, that's equal to a negative, all right, well, that would be like A double prime being negative. And if the R graph has a slope that's equal to a positive, then the graph for A is going to be concave up. And if you're at a critical point, then that's going to be a minimum. Speaking of second derivatives, if you're trying to find an inflection point, the first thing you would do is look for possible inflection points. I think we called them contenders, where the second derivative was equal to 0 for A. And then you'd be trying to find places where the second derivative changes sign. We wouldn't really care whether it goes positive to negative or negative to positive, but it would have to fully change sign in order for that graph to be changing its concavity and for us to say, oh, we've got ourselves an inflection point. Now, the equivalent story with R, easy. R prime would have to equal 0. So if you're looking at a graph of rate, there'd be a little flat spot on it. And then the actual confirmation that it's an inflection point, well, you'd be watching this R prime, which is the same thing as A double prime, and you'd be looking for switchovers. So if it switched from positive to negative, or if it switched from negative to positive. If the R prime did that, then you would know that the graph of A would have an inflection point. Okay, we're going to try this out with just 2 examples. They're not super short examples. They each go for a couple of pages, but we can actually give this a good try. So this first one is a story about some sort of fuel tank or oil tank. And like my little picture here, it's got one pipe to it where I could actually flow fuel in, or I could flow fuel out, or oil, I think it is in this story. So a single pipe would be great for either filling or for draining. And what do they say? The rate at which oil moves in and out of the storage tank, measured in meters cubed per hour, is given by this expression. And we're going to go for 6 hours. Oh, and then there's a little initial condition. They said, by the way, there is a little bit of oil in the tank at the very beginning of the day. There are 40 meters cubed in there. First thing, they said, can you go and sketch the rate? I think the whole intention here is let's just use our graphing calculator to do that. Let's get our window going right away. We need to go from 0 to 6. Maybe tick marks every 1 would be great. And for y's, looks like we might have negative rates going on here. So negative 40 And it looks like we're going up to about 120. Tick marks every 20. Okay, let's go and actually put in this function here. What have we got? 4t cubed. Well, I'll go 4x cubed. And then minus 24, I'll go x squared. And plus 12x plus 40. Okay. Oh, interesting. So we've got a positive rate for a little while. Looks like for the first 2 seconds. And to be honest, the reason why I wanted to sketch this really wasn't to precisely figure out the value. So don't worry if you get it exactly right. It was really just to find these crossovers. So right here at time 2 hours, we're actually going to switch from a positive rate and then go down into a negative rate. And from time 2 all the way until time 5, it looks like we're going to have a negative rate. Okay, it kind of dips down into here. And then, well, then a lot of positive rate just for the last hour. So thinking about this R, this rate, in terms of the in and the out, if you've got a positive value for R, then that means that you're actually filling the tank up. But if you've got a negative value for R, then that means we're actually going to be draining the tank, taking material out of the tank. So it looks like all in this section in here, during this whole time in here, we're actually filling it up. Now, let's talk about this section right here for a minute, because I know a lot of people, when they first look at this, they go, well, wait a minute, hang on, it's going down, it's going down. Well, the fill rate's going down, but we're still filling it. It's kind of like that faucet on the bathtub, where it's like, oh, okay, well, what if I'm filling it really aggressively, and then I decide, well, maybe I won't fill it quite so aggressively. I'm going to drop down my filling rate to just something a little smaller. I'm still filling it. I'm still adding more water to the tank. So the tank is still being filled. It's still actually going up for its overall level. So we're filling here, and then for the next few hours in this section in here, that's when we're going to be draining the tank. Looks like we're aggressively draining it here, and then a little less in this section, but all in there we're draining. And then for the last hour, looks like we're going to go back to filling the tank again. So filling, draining, and then filling. Okay, what do we got? First question. How much oil is added to the tank in the first 1.5 hours? Okay, well, they only want to know how much was added. They didn't ask how much was in there overall. Now remember, there were 40 cubic meters in there at the beginning, but apparently this story doesn't care about that. It's just like, no, how much was added? So going back to our little cover page here, that would be the top story. How much more are we going to put into the tank? Okay, that's all we're looking for here for this first thing we have to go and calculate. So that's just going to be a change in amount. All I have to do is just integrate from this time of 0 at the beginning to 1.5 hours at the end, and I'm just going to integrate the rate dt. So I would just be integrating 0 to 1.5, and I'll just take this rate, right? It's right up there at the top of the page. 4t cubed minus 24 t squared plus 12t plus 40 dt. Now I could do that as an antiderivative if I had some time, but nobody is saying that I have to do it that way. It doesn't say do it analytically. So I would just grab my calculator and say, hey, calculator, help me out. Do this derivative, please. And just let it have it, and it'll do it. And when I did that, I found the answer was 51.5625. And the units, it sounds like we're using meters cubed for volume. So that's what I would have there for my amount. So that's how much I added to the tank. Remember, there was actually 40 in there at the beginning, but we're going to add another 51. All right, part C. How much oil is in the tank at 2 hours? Okay, well, similar question, but now we're going to have to factor in that there is some oil in there at the beginning. So this one is a spam. All right, we're going to have to do the start plus the accumulation method. If you want to know how much there is in there at time 2, you're going to have to take the amount at time 0 and then add on. So start plus accumulation from 0 to 2. That's what I'd have to do. So the amount at time 2 would be the 40 that's in there originally, plus the new oil that goes in, the integral of the rate from 0 to 2 dt. So the R is just this same thing. I don't want to write it all out again, right? It's just this. They gave me that expression at the top of the page. Instead, I'd rather just kind of talk about the numbers. I have the 40 that's in there originally. And then when I ask my calculator, hey, can you integrate that rate? It does a nice job of it. And it says, yeah, 56 actually. Okay, great. Then the actual amount of oil in the tank at that 2 hour mark, it was the original 40 plus the 56. It's going to be 96 meters cubed. Part D. Can you find the amount at just any time t? Well, now I might not be able to use my calculator so well. I'm still going to do a spam method, but I'm going to have to do this analytically. So that's going to look like this. The amount at just any old time t, like that way people can put whatever time in they want. Well, I'm going to do a spam method, so it's going to be the start plus whatever I would accumulate from the start all the way down to just time t, integrating that rate dt. Okay, let's see if we can squeeze this in here. We're going to have to go 40 plus an integral from 0 to just generally t of 4t cubed minus 24 t squared plus a 12t plus 40 dt. I guess I do have to do an antiderivative here by hand. I've got my 40, and now antiderivative. This one's not too bad. This would be t to the 4th. This is going to be a t cubed with a 1/3 little bodyguard there. Okay, so an 8 t cubed plus, this will be a 6t squared and a 40t. And I'm going to evaluate that at 0 and t, and I always go final minus initial, so I'll put the t in for t, which will just look exactly the same, and then I'm going to put 0 in, which will be nothing, and okay, I think I can see this here now. The amount at any time t that you want to check would be 40, the original, plus, now again, when I put t into this, it'll just look the same, and when I put 0 in, I get nothing. So I would have t to the 4th minus 8 t cubed plus 6 t squared plus 40t. That's a machine that'll tell you the amount anytime you want to go and check it. Okay, so far so good. Now what do we got for the rest of this problem? Over the page, find any relative minimums and maximums for the amounts of oil in the tank over the 6-hour time period from 0 to 6, and then justify your answers in there. With a little practice, you'll get very good at just looking at that graph of rate, this graph here, and knowing how to spot little relative minimums and maximums for the amount, because we're talking about minimums and maximums in amount, not in this graph here. Looking back just at what we had up here at the top of this page, right? If we're trying to find these minimums and maximums, we really want to be focused on the derivative of A, the amount, but A's derivative is just R, right? So this is actually going to be pretty nice to do. But just, going a little slower here on this first one, kind of thinking about this the same way we would have done it back in chapter 4. We might want to think about, okay, critical points. Are there any of those? Any critical points for A, right, for amount? Well, if there are critical points for A, then A prime, otherwise known as R, would have to either be 0 or does not exist. Well, I don't see any does not exists, but I do spot some places where A prime, the R, is actually equal to 0. Okay, looking back there, I can see that that happened at 2 and at 5. So I could do my usual little game. I could make myself a nice little interval table. I'm going to have some time intervals in here where I can go and take a look at what's happening to the amount. Especially if I had to justify answers for why things were minimums or maximums, this could be really important to have. All right, so we're going to have a couple of cuts in our timeline, one at 2 and then one at 5. Okay, so this will probably work fairly well. Let's see if I can move this down just a touch. There we go. Okay, so intervals, time intervals. I've got an interesting time at 2 and an interesting time at 5. I've got all the times from 0 up to 2, and then from 2 to 5, and then from 5 until I get to 6. And I would normally be saying, oh, okay, I've got to really think about A prime here, the derivative of A. But that's just R. It's the picture that we've already sketched. And we've seen that that picture is 0 at time 2, it's 0 at time 5. But just looking back at the picture, I mean, I can see it. It's right here. I don't have to do any crazy tests. I can see, oh yeah, from 0 to 2, R is positive. Between 2 and 5, it's negative. And then it goes back to being positive again for R, which is A prime. So positive, negative, positive. Oh, okay. Well, then A, the amount of water in the tank, must have been increasing. And then here it's decreasing. And then here it's increasing again. And as far as trying to spot minimums and maximums, you'd be, when you're justifying things, you'd be talking about the derivative, saying, wow, did you see the derivative make a switch from plus to minus? And whoa, did you see the derivative make a switch from minus to plus? Hey, you're gonna have a maximum amount of water here, and you're gonna have a minimum amount of water, or oil, I guess it was, there. And that's basically our plan, right? I know I've got a local max at 2, and if people say justify it, well, the derivative, otherwise known as rate, switched from positive to negative there at 2. Now, I should maybe consider the endpoints as well, because it does have these equalities there for time 0 and for time 6. So I might want to spend a moment and actually go and calculate some of these amounts, like how much oil is there at time 0? How much oil is there at time 2? How much oil is there at time 5? And how much oil is there at time 6? Well, they told me that at time 0 there were 40 cubic meters of oil. They said so. And we've already figured out in part C that at time 2 there was 96. And in part D, we went to all the trouble of coming up with this cool machine that'll actually let you figure out the amount at any time. So I might want to use that twice more. Once at time 5, when I know there's a little local minimum, and then again at time 6 at the end point. And at time 5, when you try that out, there are 15 cubic meters of oil in the tank. And at time 6, because we've been filling for an hour, it's up to 64. So just kind of thinking about how those endpoints come into play, yeah, it looks like we're actually we're gonna start off with a minimum, a little local minimum. We're gonna go up to a little local maximum, down to a local minimum, and then up to a local maximum. And we've already kind of done all the legwork we need to do for part F, which says, hey, can you go and do a little check for absolute maximums and minimums on this hard-edged closed interval 0 to 6. Okay, well, I know there will be an absolute max and an absolute minimum amount of oil if it's got a closed interval for my time check here, right? So that's kind of nice. It's actually the extreme value theorem that says if you've got a closed interval, there will be a local max and a local min. And our usual plan for doing these absolute stories, and again, we've done the work already up there in part E, but our usual plan is find critical points, and also check endpoints. Well, we've done that. We have already done that. We have gone and checked all the interesting numbers. We checked out the amount at time 0. We got 40. We checked out the amount at time 2. We got 96. We checked out the amount at time 5 and got 15. And then we checked out the amount at time 6 and got 64. So if you want me to go and find absolutes, well, I'm done. Like this 96, that was pretty darn impressive. That's my absolute maximum in this story. And the 15, well, that's pretty darn unimpressive. That is the absolute minimum in this story. Sketching the graph? Sure. Yeah, I can do that. I can do a really rough sketch just by putting in these local minimums and maximums. So we begin with 40. And then at time 2, we're up to 96. So that's up here. At time 5, we're down to 15. And then at time 6, we're up to 64, somewhere in there. I could even use my calculator to do a more accurate version of this story. But if it's just a sketch, this is probably fine, right? It's going to go up. And then we're going to go and have a minimum. And then we're going to have a little local maximum. So we've got an absolute max right here. There's an absolute minimum here. There's a little local max, and it's an endpoint, right? That's just how they work. It was climbing, 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 and then it went stop. So it is a maximum in that neighborhood. And for the same reason, there's a little local minimum there as well, right? In that neighborhood of the graph, that's as low as you can go. Now, in this story that we're just finishing up, we had some sort of container for oil, and we were with one pipe flowing things in and out. The only difference we're going to look at now for the last story that we're going to do is, well, what if there are two distinct pipes? What if you've got a bathtub and a drain where water can go out of the bathtub through a separate pipe? So in that case, you've got kind of two different rates. You've got an entering rate where material's going into your tank, right? Maybe I'll call that E instead of R. And then I've got my leaving rate where water is going to go and leave the tank. Maybe I'll call that L for leaving. And the overall flow rate in and out of the bathtub will be some combination of entering and leaving. It's kind of nice, actually, when you have access to the math models, the equations for both the entering and the leaving. So here's the story, right? You got your faucet over here, and you've got a drain as well. The net flow rate, the overall R, it's a competition between the faucet and the drain. And so it's actually the entering rate, which depends on time, minus the leaving rate, which will depend on time. And if you want to find changes in amount, well, normally I would say, hey, just integrate the rate, dt. Well, here we're going to have to integrate this competition between entering and leaving, right? You have to do that subtraction of those to see overall whether we're actually having a positive or negative rate overall, and we'll integrate that with respect to time. So here's a little story. It's not about bathtubs, it's about bees. It says a colony of honeybees finds a small patch of flowers in a field. Over the time interval from 0 to 10 minutes, bees from the colony both enter and exit the patch of flowers. And at time t equals 0, we're going to say that there are no bees in the patch of flowers. So we've got two different rates here. The rate at which bees enter the flower patch is given by this pretty complicated looking function there. It's called a Gaussian. It's kind of got a neat little bell shape to it. And then the rate at which bees leave the patch is given by a slightly different Gaussian. And part A says how many bees enter the flower patch during the time 0 out to 4.25 minutes. Okay, well, the neat thing about having the entering and the leaving as two separate functions, two separate equations, is that we could talk just about bees entering or bees leaving. So if you only want to talk about bees going in, not like the overall rate, because they will start leaving pretty quick, right? If you only want to know how many went in, then what I could do is just integrate the in amount. So I'm going to go from 0 to 4 1/4, and I'll simply integrate that fairly complicated looking function there, that e dt. So I'm going to go to my calculator to do that. Let's see what that looks like. I'm going to graph these right now. I know on the next page we're going to sketch them. But I think it'd be kind of handy to have these as a graph. I think it would be good. So looking actually at the next page, no reason why we can't look ahead here a little bit. Here's a good window for the rates. Let's go from 0 to 10 and an up and down window from 0 to, we'll try 200. Tick marks every 25. Okay, great. So let's go and put in this entering rate just to see what the graph actually looks like. So we got 200 times this exponential, and that exponential's got a fraction in there. It has negative, open up a bracket, x minus 4 squared divided by a 1. You may go, why are you dividing by 1? It's just kind of standard practice with this Gaussian shape. Okay, let's see what this looks like. Oh yeah, okay. So there's kind of a peak time of the day where those bees are just really flying into the flower patch. And that's actually at time, looks like at time 4. Okay, so that's actually maybe worth drawing in here. Just really quick. Looks like we've got this peak value of actually 200 bees per minute entering at time 4. It kind of goes just like this. Okay, fair enough. Got that. And that rate is actually in bees per minute. And that's my entering rate. Awesome. I'm going to put the other one in too just while we're at it, just so we have them both. So the leaving bees, they have a slightly different leaving rate. They're 100, then an exponential, e to the negative. We'll open up a bracket. X minus 6, and that's squared, divided by 4. If you want, you can put the multiplication in here. It doesn't have to be in there. It'll do it anyways. Okay, so what does the leaving bee rate look like? Okay, it's a broader peak. It's later and it's lower. So it's actually peaking at time 6 Maybe I'll do a little darker color here for you. We'll go purple. And it's a bit broader looking. It's kind of like this. So that's the leaving bee rate. Okay, well, back to our question. They were saying, hey, how many entered from time 0 to time 4 1/4? This graph here is bees per minute. It's not bees. I'd have to integrate. So I'm going to say, hey, calculator, can you please integrate option number 7? And it's asking me, well, which graph, right? Y1? Yeah, I want to do Y1. That's the entering. From 0 to 4.25. Yeah, it thinks about it for a minute, and it goes, yeah, I can do that. Okay, whoa, that's a lot of bees. We can round to the nearest bee. Looks like 226. So all we've done is just integrate the rate. And if you want to know how many went into this little patch, just integrate the entering rate. So 226 bees. What do we got next here? Every bee leaving the flowers carries 0.15 grams of pollen. How much pollen is removed from the patch? By all the bees, I'm assuming. By the time T gets to 7 minutes. Well, let's go and find out how many bees leave the patch. Right? I kind of like this idea where we've got separate equations for the in and the out rate. So if I want to know how many bees, the actual amount that have left, what I could do is just integrate from 0 to 7. Sorry, getting ahead of myself here. From 0 to 7, I'm going to integrate the leaving rate, dt. Okay, calculator, you're up. If you ever want to clear off the black shading, all you have to do is just ever so slightly change the window. Like you could say, oh, how about I go to like 210, right? And then when it redraws it, it'll get rid of all of that shading. So there's the entering bees. Here's the leaving bees. And I want to integrate that leaving rate to find out how many have left over 7 minutes. So calculate option number 7. Oh, I'm going to go down an arrow because I don't want Y1. So just, say Y2. And let's go from 0 out to 7. No bees had left at the beginning, right? So we'll just start right here at 0. Let it integrate out to 7. That's a lot of bees. 269 bees, almost 270. 269 bees have left. There's another one that's just like, I'm almost out, but it's not out yet. So 269 bees have left the patch. But each one of those bees has got a little bit of pollen on board. So we can go 269 bees times 0.15 grams. And it looks like they've carried away 40.35 grams. So pretty handy having that option to have the entering and the leaving separate. Okay, got the graph done already. Invested that time early. D, when is the number of bees in the flower patch a maximum? And then justify that you know that this time is a maximum. I want to first show you the common mistake that people make. A lot of people go, oh, you want to know when there's the maximum number of bees in the flower patch? I'll go right here. And that's wrong, right? That is not the time when there's the most number of bees in the flower patch. And you look at it and you go, well, there's a peak in the graph. But that's actually just the entering rate. If you were to think about this in terms of a bathtub, that would be when you've actually got the most serious flow of water in. But you got to remember that there's a competition going on between the entering and the leaving. So sure, you may have found the moment when you've got the biggest flow in, right? But well, what's going on with the leaving rate? You know, if I look back here, sure, there's a big flow in, but I'm not really draining very much at all, right? The drain rate's pretty low. So that would look kind of like this story, right? Where it's like, oh yeah, there's a little bit leaving, but it's, you know, it's pretty minor, right? And okay, yeah, sure, we're definitely going to be, you know, seeing more bees come in than come out. If I go a little bit farther in time, if I move down to say here, sure, the rate at which it's going in is not as serious, but it's still better than the leaving rate that you'd have right there. So I think we're still doing better, right? Thinking about this in terms of the bathtub, that's like saying, well, let's turn this faucet down just a little bit. Okay, we won't flow quite that fast. I'll drop this down to like here. So erase that super thick arrow. It's like, okay, well, it's pretty good, but it's still better than our leaving rate, right? So my leaving rate, got some little arrows here that aren't quite as thick yet as that one. So we're still gaining ground. We're still having more flow rate in than out. The time when you're going to hit a maximum is when this flow rate into the tank right here is equal to the flow rate out. Right when they're equal, that's when the bathtub's kind of got a stable level to it. And then when the drain starts to outperform the faucet, then the water level will go down. So as long as the faucet is outperforming the drain, we're still seeing the bathtub go up. And the same thing is true with the bees. As long as the entering rate is outperforming the leaving rate, then we're still gaining bees. So even in the time like right here, we're still getting more and more bees in than out. But then all of a sudden there's a crossover. Now the leaving rate, it's like the drain outperforms the faucet. And so the maximum moment of bees for this flower patch will actually be right at this crossover point, which is not exactly at time 5. It's close, but not quite. But that's when you're going to have the maximum number of bees. So they're like, yeah, go ahead, get that time and then justify that you've got a maximum. I'm looking for that crossover moment. I can actually just ask my calculator to do this. Again, I'm going to change my window back, just make it look a little nicer here. I'm just going to say, hey, calculator, these are complicated graphs. Can you find out where they intersect for me? And it'll do it. It's really close to time 5, but not exactly. So I'm going to say, hey, calculator, let's do an intersection between that graph, and yeah, it's right around there. Okay, 4.9771. That's the time. I want to remember that time, so I'm just going to quit here for a minute. I suspect it's right here in X. Yes, it is. I'm going to store that in A because my calculator tends to overwrite what's in X. All right, I've got it. Okay, so I found the time, and they're like, well, can you justify it, that that's actually the maximum? I would say things like this. If the amount is a maximum, right, if A is a max, then I know that A prime switches from positive to negative at that time. But wait a minute, there's some nice little conversions here. A prime is the same thing as just plain old rate. It's just R. And in this story, R is just entering minus leaving. So we want entering minus leaving to switch from positive to negative. And that's going to happen right there. Okay, that'll be that moment. Part E says, okay, well, what is that maximum number of bees? Okay, well, if you want to know the maximum number of bees, then what we should do is we should integrate. Remember, there are no bees in there at the beginning, right? So the amount in there at that time, 4.9771, if I just do a spam with this, there are no bees in there at the beginning. And then I'm going to integrate from 0 to 4.9771. I'm going to integrate the entering function minus the leaving function, dt. I can actually do those separately even if I want to, right? It's actually kind of neat to see. So go back to my graph here. I'm going to say, okay, calculator, can you tell me, by integrating, I'm going to do y1, the entering, lower limit 0, and upper limit, I stored it in A, right? Okay, so this is going to figure out how many had entered up to that maximum moment. All right, 325 had entered. And then the leaving ones. So calculator, please calculate. Number 7, I want to switch functions and say, okay, from time 0 to time 4.9771. I'm doing this because it's neat to see the number of bees that have entered and left. 325 had entered at that moment, and 83 had left, for a grand total of 242 bees still inside the flower patch. And the other reason why I did it that way, to do it separately, is because it was just easier for me to do, to be honest. I didn't have the patience to type in the entering minus leaving into some integral in my calculator. So I just said, hey, calculator, please do that whole thing. Last part says, can you sketch the graph of the amount of bees in the flower patch at any time? Sure, yeah, we can do that. It really kind of taxes my calculator to do this, so I might have to give it some nice way to do this. I do have these functions in already, so maybe I will do this. I'm going to say, okay, math, can you go, it's number 9 for me, can you do an integration? It's like, yeah, okay, an integration of what? Well, I want to do like the y1 minus the y2. So here we go. Variables, entering minus leaving. I'm using x's. Can we go from 0 to, and then we can put various numbers in here. We've already seen the answer for really close to 5 was 242 bees, right? That's when we hit a nice little maximum here, right around there. Okay, let's try some other numbers. What about at time 1? Don't ignore the negative. I know that doesn't make any sense. These little shapes that I've picked, it's kind of weird. I'm cheating a little bit, so I got to be honest with you and tell you what went wrong here. Way back out here, the leaving graph gets a little bit above the entering graph. It's just a nature of the shape because it's so wide. So my math modeling here is not really perfect. So let's not look too closely at that. Let's move down the road maybe to time 2. That's my fault. Just bad bee modeling. Okay, so even at time 2, we still really don't have any bees in the flower patch yet. They just haven't found the flower patch. So, basically no bees, basically no bees. Let's try it again, and we'll go out to time 3. There's a competition between entering and leaving. Ooh, and right now we've had about 22 overall stick around in this patch at time 3. More have come and a few have left. So that puts us, I don't know, somewhere around there. We'll try it again out to time 4. They pretty much all find this flower patch at once. So when you get to time 4, a whole bunch will have arrived and some will have left already. And we're up to 149. So right around here. We kind of know what 5 looks like. Let's look at 6. And this is actually pretty typical for, work with integrals. Often you just get your calculator to do those integrals for you. 176. So we're up. What does my scale look like here? So 150, 176, somewhere in here. Okay, just a couple more to do. At time 7, a whole bunch of bees will have come, and a lot of them will have left. And at time 7, there are still 85 bees in the flower patch. Yeah, they're all starting to leave now. Kind of looks like almost like an amusement park as well, right? Where a whole bunch of people arrive at the beginning and then they start leaving. And later on in the day, there are more people leaving than there are entering. Okay, we'll try this again, just a couple more. At time 8, really no more bees entering. They're just all slowly leaving. 27. Somewhere in here. Six. Not many. Is there even one left at 10? Let's see. Moral of the story, it's kind of nice when you have entering and leaving rates, because then you can play games with like how many have entered, how many have taken pollen away. It's a little more interesting when you're looking for maximums for amount. One last bee. Because you have to think about that competition between the faucet and the drain. And that's going to finish up our first lesson for this chapter. And the next lesson, we're going to look at just different ways that you can be, integrating things in order to find some amounts.